Hello junior techies, and welcome to this video in which we will be solving problems involving molecular polarity. Or in other words, we will check to see if whole molecules are either polar or non-polar. In order to successfully do so, we need to have knowledge of Lewis diagrams. We need to know how to determine the type of bond that exists between two atoms. And we need to know how to use valence shell electron pair repulsion theory, that is VSEPR theory, in order to determine the shapes of different molecules. Those concepts are necessary in order to determine the polarity of molecules. So junior techies, if you have any trouble with any of those topics, please go and watch the other videos in this series in which I do my best to explain those concepts. In this video, we are going to be solving two different problems, this and another problem. This problem says, explain the difference in polarity between carbon dioxide and water by referring to the polarity of the bonds and the shape of the molecules. So we need to decide if carbon dioxide is polar or non-polar, and we need to do the same with water. In order to do so, we're going to be following the steps that you will find in your theory booklet. So make sure to download and read through the theory booklet that you can find on the Junior Techie website. We're going to start off by analyzing carbon dioxide. We draw the Lewis diagram for carbon dioxide. And to make our lives slightly easier, I am going to replace the bonds between carbon and oxygen with straight lines, as you do in a Cooper structure. Now that we have a diagram to analyze, we grab out a periodic table where we find that there is a difference in the electronegativity between carbon and oxygen. All that this means is that the bonds in this molecule are polar bonds. And since we have polar bonds, we need to take things further and determine what type of shape the carbon dioxide molecule has. We complete the general formula, which in this case becomes AX2. And this tells us that we have a linear shape. We now need to find out if carbon dioxide is symmetrical or asymmetrical. So we use arrows to point towards the more electronegative atom in each bond. In this case, the more electronegative atom is oxygen. And if you look at these arrows, they point in different directions, which tells us that we have symmetry. We also notice, though, that the oxygen atoms, the terminal atoms, are exactly the same. They both have the same electronegativities. And based on this, we can conclude that the carbon dioxide molecule is symmetrical. Bringing all of this information together, the fact that the bonds are polar, that the molecule has a linear shape, and that the molecule is symmetrical, we can conclude that carbon dioxide is a non-polar molecule. We now need to follow the same steps for water. So we start off by drawing its Lewis diagram, and once again I will replace the bonds with straight lines. Using the periodic table, we find that the bonds are polar bonds. So we now determine what type of shape this molecule has by completing the general formula. Here we have AX2E2, where E represents the number of lone pairs on the central atom. Using this, we determine that this molecule is bent. You may also refer to it as angular. Now that we know the shape of the molecule, we can determine whether it is symmetrical or not. And we do so by firstly using arrows to point to the more electronegative atom. We notice already that there is not symmetry, but also, since there are lone pairs on the central atom, the molecule has a non-ideal shape, And this is information enough to let us know that the water molecule is asymmetrical. Bringing together the fact that the bonds are polar, that the molecule is bent, and that the water molecule is asymmetrical, we can come to the conclusion that the water molecule is a polar molecule. But, junior tickies, we now need to explain this in words. So we say that both carbon dioxide and water contain polar bonds. That is what is similar about them, but we explain this, we write this down because the question refers to the polarity in the bonds. The question also refers to the shape of the molecules. So we now state that, however, even though they have polar bonds, both of them have polar bonds, carbon dioxide is linear and symmetrical, while water is bent and asymmetrical. This is the difference between the two molecules. And because of this, we therefore say carbon dioxide is non-polar, while H2O, the water molecule, is polar. Having written this down, we've completed the first problem. But just to take things a bit further and make sure that all of you understand what is going on and what we mean when we refer to the polarity of a molecule, I would like us to go back to the Lewis diagrams. And if you look at the whole water molecule, the fact that it is polar just suggests that on the side where our oxygen atom is, the molecule will be slightly negative, while on the other side it will be slightly positive. This is one of the reasons that water is such a useful substance to humans and all life here on Earth. If we look at the carbon dioxide molecule as a whole, there's an even distribution of electrons, and it is for this reason that carbon dioxide is non-polar. We can now move on to the next and last problem contained in this video. This problem says, boron trichloride and ammonia both contain 3 bonds around the central atom. The boron trichloride molecule is, however, non-polar, while the ammonia molecule is polar. Account for this difference between two compounds using VSEPR theory. And I would like to remind you that VSEPR theory is just valence shell electron pair repulsion theory. This question is similar to the previous one, except here they have told us already that one molecule is polar and the other is non-polar, and we need to explain why it is so. So we're going to start off by analyzing each molecule as we did in the previous question. So we look at boron trichloride, we draw its Lewis diagram, and once we have completed the Lewis diagram, we can replace the bonds with straight lines. We now need to determine if the bonds are polar or non-polar, and since there is a difference in the electronegativities, we know that the bonds are polar bonds. Using the general formula, we find out that boron trichloride is trigonal planar, and we now need to determine if our molecule is symmetrical or asymmetrical. Trigonal planar, when a molecule is trigonal planar, it doesn't look so much like the Lewis diagram that you currently see on the screen. Instead, the bond pairs are more or less an equal distance from each other. And based on this, you should notice that when we draw in the arrows show that the molecule is symmetrical, but also all of our terminal atoms are chlorine, so they have exactly the same electronegativities. And because of this, we can conclude that the boron trichloride molecule is symmetrical. Bringing together the fact that the bonds are polar, that the molecule is trigonal planar, and that it is symmetrical, we can conclude that it is in fact a non-polar molecule, as the question says. We can now analyze the ammonia molecule using the same steps. We start off with its Lewis diagram, and I'm going to replace those bonds with straight lines. We now see, using the periodic table, that the bonds are polar bonds. We complete the general formula and find out that this molecule, this ammonia molecule, has a trigonal pyramidal shape. We now need to determine if the molecule is symmetrical or if it is asymmetrical. All of these arrows point towards nitrogen because it is the more electronegative atom. But notice that there's a lone pair on the nitrogen atom, on the central atom. And because of this, we have a non-ideal shape, and we come to the conclusion that the ammonia molecule is asymmetrical. Bringing together the fact that it has polar bonds, that it is trigonal pyramidal, and that it is asymmetrical, we can come to the conclusion that ammonia is in fact a polar molecule. We can now answer the question in words, but to do so, we need to make use of VSEPR theory. Remember that this theory simply states that lone pairs repel other lone pairs and repel bond pairs more strongly than bond pairs repel each other. So we need to make mention of this somewhere in our explanations. We start off by saying boron trichloride has no lone pairs on its central atom, so it is trigonal planar and symmetrical, causing it to be non-polar. On the other hand, the ammonia molecule has one pair of lone pairs on its central atom. Since lone pairs repel bond pairs more strongly than bond pairs repel each other, the ammonia molecule is trigonal pyramidal and asymmetrical, causing it to be non-polar. In writing this down, we have solved the problem. But again, I would just like to make sure you understand all of this 100%. So I'd like us to go back to those Lewis diagrams and show you that the fact that ammonia is polar simply means that on the side where we have the hydrogen atoms, the molecule is going to be slightly positive, while the side where the nitrogen atom is will be slightly negative. Boron trichloride, on the other hand, has an even distribution of electrons, and based on that, it is a non-polar molecule. Junior Tikkies, I hope that you have learned everything that you wanted to learn when you clicked on this video. I'd like to remind you that there is a worksheet and a memo to that worksheet on the Junior Tikkie website. So to reinforce all of the ideas that you have learned in each of these videos, go and download that worksheet, work through it, mark it with the memo, and in doing so, you will be able to turn your short-term memory into long-term memory so that you can apply it in your tests and exams. I wish you all the best for the week ahead. Thank you for watching this video.